So this presentation is about showing that actually you can fit a lift full of people. So there were two co-authors in the article, Mirko Ruokokoski and Marja-Liisa Siikonen, and Marja-Liisa just wanted to say a couple of words as a background before going into the subject.
Yeah, just a few words why we have this paper here in this conference is that there is a third standard coming in addition to PCO and SHIPSE of elevator selection, and it's ISO. And there, I'm the chair, and many people in this room are members of this group, working group. The aim of this code is to make a standard that is quite in line with the old method that has been used for 60 years or more, given the right number of elevators, and we want this standard to be in line with that old practice. And now there is a slight problem with this actual capacity if we use it as an input to the analysis. So for instance, if you think about 1,600 kilogram car that has been used for 21 persons, and we have had the right number of cars, then if we now use the actual capacity of 16 persons as an input, so it will result in a different number of cars, and it's not in line with the old practice. So we made a study how to get these two things in line, and Janne shows the result of the study.
Okay, thanks. So it's going to be like this if the lift car is full. This is a picture of an old Otis experiment, probably from the 1960s. So it doesn't look too comfortable. At the back of corner of the room you can see 1,000 kilo elevator lift. So you might want to try whether you can fit 13 persons in that car. We tried that on Wednesday in CHIPS meeting, or after CHIPS meeting. Okay, so the presentation has these contents. So first some background, then I introduce the body ellipse concept that can model lift passengers, how much space they occupy, and then try to find an answer to the question that how many passengers can actually fit the lift. And then introduce this area per passenger, how it could be used as service quality criterion. Okay, so as a background, passenger capacity is just the maximum number of passengers that the lift can accommodate. And now, as Marja told, there are two different ways to define it. The first one is the safety standard based definition, where the rated load is divided by the average mass of the passengers, 75 kilos in EN81. That's one. And then there's this area-based passenger capacity, which divides the maximum allowed area by 0.21 square meters. And why then these things matter? This area-based passenger capacity is something like 59 to 90% from this load-based passenger capacity. And this causes, of course, that the handling capacity calculations give completely different results. As what was already showing, that saturation in the lift group happens at 80% utilization factor, or what was your term? Loading. No matter how it's defined. And this number is related to the maximum number that actually is put in the lift. So this definition is important so that you get this old and new analysis in line. So John KONE introduced in 1970s the body ellipse concept, which was based on a 95th percentile male at that time. And such a person used to weigh 90 kilos. So here you can see the body ellipse, which has the width of 600 millimeters and depth 450 millimeters, and it already assumes some space around the actual body. So after all, even if these kind of ellipses hit each other, still the bodies do not touch each other in the analysis. So here you can see the distributions of male and female body widths, and this 95th percentile man is here, and this 95th percentile means that 95% of all men are smaller than this particular one. And then of course all the females are also smaller than this one. So, and the averages are of course quite a lot less than this 95th percentile. Now this one actually was weighing 90 kilos at the time this was done, but now these safety standards are based on an average passenger weight of 75 kilos. So then the question is that is it reasonable to use this body ellipse as the basis for lift traffic? Okay, so here are the different dimensions of the 95th percentile male, and then also average and male and female, and here they are drawn in scale inside the body ellipse. So you can see that there's quite a lot of space around the body itself. So the original body ellipse is quite big compared to these ones. And here's just a proposition of smaller body ellipses, which are derived in the same way as the twin original body ellipse, that has the same amount of space beside the body itself and also in front and back. And the areas of these ellipses are quite different from this twin body ellipse area. So, for example, for males it's 0.177 square meters. And of course you can calculate passenger capacity with all these different kinds of ellipses. And now when using this twin male body ellipse, passenger capacity would be 20 persons, but if you take an average of male and female, it would be 26. And this is now a 2,000 kilo lift for which this one is done, and for that the EN 81-1 gives also this 26 person capacity. So then how many passengers actually can fit into the lift? Since this way how this area-based capacity is defined, it assumes that this area of the passenger is a rectangular area, not an ellipse. That's why we formed actually a nice optimization problem that tries to find how many ellipses one can actually pack within lift dimensions. And the idea is just to minimize the sum of overlapping areas of the body ellipses and body ellipses and walls. And here a short description how the optimization works. So first there's dimensions of the lift car. So these ones are now the dimensions of this 2,000 kilo lift. And in the beginning there are the ellipses describing passengers are just put randomly in that space. And here are then overlapping areas the ellipses and the walls. And after this, the optimization is executed, and as a result, it changes the coordinates of the ellipses and also the angle against the axis, so that the ellipses either fit in or not. And in that way, we could find out if the particular number of ellipses can fit in this certain lift car. So, and the question is that can we really fit 26 passengers into this 2,000 kilo lift? First we tried these front body ellipses, and the result was that only 15 of them could be fit in the car. And that's because there always needs to be some space between the ellipses, since it's not a rectangular area. Then we took randomly body widths from a normal distribution, and also a mixture of females and males. So here the blue ones represent males and the orange ones females. And also, and in this case, we also assumed less space inside the body ellipse, and which in a way corresponds to the situation that when people really try to load and back a lift, then they actually touch each other a little bit. And this was something that was also experienced in this Wednesday experiment. And as a result, we found that all these 26 ellipses could fit in the car. And then, how this then relates to this actual experiment of Otis in the good old days. So, in that experiment, they could back people in a density of 0.167 square meters per person, and well, it's really tight. And this is pretty close to the result of this our mathematical experiment, where the occupancy was 0.153 square meters per person. But that's reasonably close to the actual real experiment. For example, if you look at this occupancy, when there was 15 twin ellipses, it was only 0.28 square meters per person. Okay, so then we'll talk how to use this area per passenger as output, or from the output results of the traffic analysis, instead of taking it as an input parameter. So KONE introduced this level of service concept in this classical 1970s book, and that is based on this area per passenger. And he divided different occupancies to 6 levels of service, A being the, let's say, the least dense one, where there's practically a huge amount of space around each people, and then level of service F, which is then very congested and uncomfortable, and also can be dangerous. But he also gave an example that this level of service E could be used to design a lift occupancy. And that range was from 0.2 to 0.3 square meters per person. Now this graph actually shows the relationship between the load factor and this cos E range. And here you can see that this loss E ranges from 60 to 80% car load of the rated load. So as the traditional lift traffic design has been based on this 80% car load factor, it seems that it's quite nicely in line with this Fruin definition. So we propose slightly refined way of doing traffic design, in which, let's say, most of the stuff remains the same as earlier, use the 80% car load factor and so on, but then take this area per passenger as an additional quality of service criterion. And that can now be actually applied to this output result. So for example, if simulation reports that elevators were loaded up to 80% car load, then immediately it is known how many people there were inside the lift, and then one can find out what was the area per passenger in that case. And now, this is just kind of an example how it could be applied. So for example, in prestige buildings, it's possible to target at least 0.28 square meters per person, and this one corresponds to the touch zone density that Fruin also defined, and that could be kind of called as comfortable loading. But then in other buildings, for example, 0.2 or 0.21 square meters could be used as a target criteria. This way, it's also possible to take into account special passenger needs like luggage or carriages, and it's also possible to use car load factor instead of area, but probably the area gives, after all, the best idea how much or what is the actual quality or service in that case. So just one quick example, which is now based on the latest draft of Gypsy. So it's a overall simple calculation to show what's the difference between this area-based capacity and this area per passenger as a service quality criterion. So it's just a simple thing to transport 100 persons in 10 round trips, when on average it's required that 10 persons are loaded in a lift for each round trip. And when this area-based passenger capacity is used as an input, the result is that the lift might be too small. But then, if you think about this traditional load-based passenger capacity of this 1,000 kilo lift, still, even if there is 10 persons inside it, there would be 0.24 square meters per person. And in that sense, that lift has enough space for these 10 passengers. So this contradiction is something that, in a way, results in these different ways of defining passenger capacity. Okay, then I'm finally ready to conclude the presentation. So, just a couple of advantages of using this area per passenger as an additional criteria. So now this area is output, not an input to this analysis, and for that we can develop ranges of this service quality criterion, and that could be applied at target passenger demand for a particular case. Another thing is that it is also contingent with earlier traffic design methodology, so you only need a very small refinement to the analysis, and need to just look a little bit more detailed at the area per passenger. It's also nicely in line with this pedestrian planning principles. So after all, lift planning is quite similar to this other pedestrian planning principles. This also is universal with respect to geographical area, building type and culture. But of course, you need to find these values for this criteria in different areas, which is then based on the actual, or should be based on the actual sizes of the people of that certain country or area. And one nice thing that I like is that it's transparent to all stakeholders. So everyone can see that what is actually the area per passenger for a certain installation. And then one can debate whether that's good or not, whether there's a need for bigger class or not. Okay, thank you.